So let's get started. We're going to continue with where we left last week. And so today we're going to finish the op-amps, and we're going to jump into chapter 3. And we're going to finish chapter 3 today. Yeah, go ahead. Chapter 2, I don't remember. It was the date.
Yeah, I believe it said.
Oh, okay. I can extend it. That's not a problem if you guys need more time. Okay. Any other questions? No. Okay. Last week the last example we had was looked like a very complex circuit for instrumentation. The idea is that this circuit would take a differential input, or it take two different inputs, and go through each amplifier, and then get your output. Now, what we did was from the beginning, we already did the process. I just want to repeat the process. You guys know how we did it. This is a water ground, which in fact did not exist in actual, so in the circuit. So what we did is we look at the terminals, and we said that, well, the terminals are going to have the same voltage. So therefore, the negative terminal over here becomes Vi2. Similarly, the negative terminal of A1 becomes Vi1. So therefore, we find the voltage between these two R1s because we know the voltage at the both up node and lower node. So the voltage difference between these two nodes divided by the resistance, we get the current in this branch. And then we said that, well, there's no current going into each of the op-amp. So therefore, the current through this R1 branch would have to go this way. Yeah. And then similarly, the other one would have to go R2 to R1. So this forms a big loop, right? So that's the first step. So this circuit basically represents the first step. So look at, we add those two R1s. Now we find the voltage over here, and we find the voltage here, and then we find the current. And then the current goes through this branch. There's no current here. There's no current over there. So since there's a current going this way, we can find the voltage already over here. And then by adding this voltage to the voltage drop on this one, we get the voltage over here. Similarly, by subtracting the voltage of that one to that one, you got the upper voltage over here. So VO1, VO2, you got it, right? And then we do the second part. So basically, this going to the next step is looking at, okay, so we find the current here is marked here, and the current here, and then we find the voltage over here, which is difference between these two. And the next step is that if you know VO2, you see, if you know VO2, because there's no current here, so you can easily find the voltage over here. Voltage divider, because there's no current here, so R3 and R4 are voltage dividers. And then once you find the voltage over here, this voltage is the same. So you find the voltage over here. Since you know VO1, so VO1 minus this voltage divided by R3, you got the current over here. And then this current going this way. So this voltage minus current times R4 gives you output. So this is the final expression. So we went through the process. We didn't write the final expression, which is this expression here. VO is 1 plus R1 over R2, R4 and 3 times VID. So VID is defined as VI1, VI2 minus VI1. And so this is where you get this whole process. It's a little bit complex in the sense that a lot of components, a lot of resistance, a lot of nodes, a lot of circuits. But the bottom line is that you need to understand the positive and negative terminal always have the same voltage. That's very important. That's one important. And the second one is no current going into each of the terminal, the input terminal. Remember these two things, you really simplify the whole process, right? So there's not much really to worry about. You can just have to do step by step, okay? Now we're going to jump into the next idea is that so far we only treat all those feedback, all this input and output terminals connecting with the resistance. I mean, in fact, we have impedance, right? So you guys know that impedance, including, for example, capacitors, and inductors. And how do you calculate the impedance of a capacitor inductor? Do you guys remember the different ways to write it? Yes.
J is like the one is J omega L.
Yeah.
The other one is J. Well, 1 over J.
1 over J omega C. Yeah. So this is the impedance, and then they both have the units of ohm. So this is the impedance of so in 2 times you most likely learn everything in terms of J omega. Omega is a frequency. So you can see the impedance property is very clear. For C, if C is very big, the impedance is very small. For inductors, if L is very small, the impedance is small. If L is big, the impedance is big. Yeah.
J is standing in for the square root of -1, correct?
Yes, it's imaginary.
Yeah.
Yeah.
So this is only in the frequency domain?
This is in the frequency domain.
Okay. And,
this is what we call it in the time domain, in fact. Yeah, time. Well, I mean, frequency domain because it's just saying J omega. The time domain will be sine omega t, sine like that. But here, yeah, it's a frequency domain. You're right. But what I want you to say is that we use J omega. So J is a square root of -1. So it's the imaginary sign. And but what I want to tell you here is that the C and L, they are opposite. So this is 1 over omega C. That's a. So in fact, some other cases they use a different C. They use a different way to express this. For example, sometimes they use J XC and J XL. In that case, the XC would equal to 1 over omega C. In this case, XL equal to 1 over, sorry, sorry, I don't know how to do this. So 1 omega L. So instead of in XL including the J, they take the J out, just make it easier. Now, you are right. Well, you're right. For XC, it's 1 over omega C. It's going to be yeah. There's a negative sign going to be yeah. Okay. Now because the J omega is kind of always there, so in the control theory, they try to do even in a different way to make it simpler. Nothing really changes. So they simply say use S to be equal to J omega. So when you have S equal to J omega, for C, it becomes like 1 over SC. And for L, it becomes S times L. So those are the impedances for inductor and a capacitor using S. Now, the reason is just to really simplify the process, because when you have a complex circuit, that you have a lot of J omegas, and when you multiply J omega to J omega, it gets J squared omega squared, right? And J squared becomes -1. Okay, you tend to replace it with -1. But towards the end, you say, oh my God, there's a J, this -1, then then you got really lost to the end, and easy to make a mistake. So by using S, you simply want 2S, just S squared, 3S, just S cubic. You don't do anything. But once you finish all the derivation, you replace S back by J omega. So regardless what the S is cubic, whatever, square, you just simply replace with J, and you simplify that J at that point. So it makes life a little bit easier. I guess somebody really smart and did this in the past. So now you go to your 420, for example, controls class, you see a lot of S. They don't use J omega. They're always S. Okay. 3-4 times probably too. You use a lot of S. But you guys are not taking that class yet. Okay. So what does it do with us? Well, let me see if I can next slide. Okay. Maybe it's I still have to put it on this slide. So if you have Z1 and Z2, now the property of the op-amp doesn't change. So therefore, we would have this one. In this particular example, we have 0 volts here, and we have 0 volts here. See, the two terminals have the same voltage. And also the other property, no current into no current into the each terminal. So therefore, we can find the current at Z1. I'm going to do it over here. So you can do it together. What is I1 into Z1? It's going to be Vi minus that voltage at the negative terminal, which is 0, right? So basically, divide by Z1. It's equal to Vi Z1. And so you know that I1 is equal to I2 because there's no current going into the terminal. So now we can find Z2, because for Z2, what we can do is we can use 0 minus VO divided by Z2 equal to I2. So now you plug R2 into this equation, you got VO equal to negative Z2 over Z1 times Vi. So there's a negative sign here. Right, sorry. So we're going to get VO equal to negative Z2 Z1 times so this is a funny equation we got. By looking at this, you already notice that there's no difference, right? When we have resistance R2 or R1, now it's Z2 or Z1. So now think about it. You can use Z1 with Z1 and Z2 in, you can use a capacitor, you can use an inductor, you can use a combination of resistor, inductor in parallel and series. So you get really like nice equations to get a different output. Now, once you got that, once you get to that point, we know that the VO is no longer going to be like a constant. If Vi is some sort of waveform, and V2 will be some sort of waveform as well, but it's not going to be the same waveform. It's or same phase or same amplitude. It's going to be different amplitude, different phase, and maybe different angle too. Okay, so that's where we're going to lead to the next talk is about. Okay, so now let's do it. So we're going to replace that R2, instead of R2, we're going to add a C on top of R2. So now R2 and C2 are in series. In parallel, sorry, in parallel. So in this example, again, we have V plus equal to 0. That's because it's grounded. So therefore, V minus equal to V plus is to 0. That's great. And then we will find I1 equal to Vi over R1. Well, the only thing that we don't know is what is the current going to R2, what is the current going to C2. The total we know is, but how much is IC, how much is I, say, R2, we don't know. But of course, you can say, well, these two are in parallel. So we can use a current divider to find the current in each branch. But there's another way to look at, because our purpose is to find VO, right? So we really don't have to worry too much about the current exactly in each of the R2 and C2. But what we can do is we can find the impedance of Z2. So Z2 is going to be R2 in parallel with XC2. Let's call it XC2. And XC2 is 1 over, so it's going to be R2 in parallel with 1 over SC, right? So, and this one, of course, you can further say, oh, this is going to be 1 over R2 plus SC, so 1C. So that's how you get this. And then you can further simplify this to be 1 R2 over 1 plus SCR. And over here, you got a very interesting, bottom of the equation is there's S times CR. And you guys probably, if I do this, you probably know what it is. Tau equal to RC. So RC is a time constant. The unit of R, ohm, times C is farads. That RC together, if you do the derivation, you'll find that they give you the unit of seconds. Okay, that's the metric value. That's the beauty of. So basically, you can write this as R2 over 1 plus S tau. So that gives you a time constant. So the next step will be we need to find VO. So now we know that VO is going to be, so again, if you guys still have trouble getting this through, you can always do this. VO, okay. So we're going to write this equation. We're going to draw this. We're going to draw it like this. I'm going to draw like that. So it's going to be 0 minus VO divided by Z equal to I2. And I2 equal to I1. So I2 equal to I1, which is equal to VI over R1. Okay, just like this. And now, so you can see that VO equal to, you multiply Z on both sides and you move the negative sign. You see that it's Z over R1 times VI, and there's a minus sign over here. Okay, so this is where we get this output voltage. So now you can plug in the Z, okay, the Z2, right? So we got Z2. Yeah. Now you can plug in that Z2 from that equation over here, you get the VO as expression. So now, of course, what happens is that depending on what type of VI you have, the VO will be very different. Now, for example, if VI is DC voltage, what happens?
Eventually, the capacitor will charge up, and then it will just become, yeah, it'll become an open, and then we just have the gain equal to R2 divided by R1.
Right. If it's a DC, which means initially the voltage cannot change on the capacitor, be 0, so it will be charged up. All the current initially will go to C2. Yeah. But as C2 voltage increase, the current will reduce, and eventually the voltage across C2 and R2 are going to be, increased to the point that we all. Okay. So now you see all the current through R1 is going to go to R2. No current going to C2. And so that's the DC. But if I is not DC, but it's AC, what happens? Well, I mean, if it's AC, then you have impedance, and you can plug it back in to get the magnitude, and then you can convert it back into time domain. And you can always do that. So it's going to be some value. But more generically, we are going to look at, this VI, like any generic waveform, and we want to find VO. So we look at this circuit that does not have a resistance unit. So looking at this circuit, we want you to find out what is VO for any given VI. Now we're going to look at different examples. If VI is DC, what happens? If VI is a sine waveform, what happens? Now we can start with a derivation of the process. Okay? So it's already marked on there. So the positive terminal is grounded. So therefore, the negative terminal voltage is 0. And current through R, you can easily find it. It's going to be I1 is going to be equal to V1, which is sigma T, divided by R. And this is equal to I2, which over here, of course, we say this is I2. And it does say that it's equal to I1. But then that one is very straightforward. But the most important step is the next step is going to confuse a lot of people. Say, okay, well, the current going to C, what happens? Now, if we remember, in the time domain, what is the relation between voltage and current on the capacitor? What is it? I equal to? Great. And of course, you guys also know the current between a voltage and a current on an inductor. So those are the very important equations. So that's in the time domain. So if in the time domain, now we're going to use this one because this one later on we're going to use it. If I equal to C over dV over dt, and what is the voltage then? Well, the voltage is going to be the integration of I, right? If it's the integration, then we have to add like the initial value. That's so from here, you got here. So let's call it VC. Yeah. So you found VC. So in this example, what is VO? You guys probably know. VO equal to minus VC, right? So VC is this way, and VO is this way. So VO is a negative terminal. VC is up there. So or you can use like 0 minus VO equal to VC, right? So VO is equal to minus VC. So if you guys have trouble to understand this, you can use 0 minus VO equal to VC. So that's how you get VO equal to minus VC. So if VO is equal to minus VC, and then this equal to minus 1 over C, integration of I1, we already found it, so VI over R dt plus VC 0. And equal to, well, we can move the R out because R is a constant. Okay. So here you guys already find out. What is it? Well, it's 1 over RC, which is time constant. And inside is VI dt. If this is 0, if this part is initial, if capacity initial voltage is 0, which is true a lot of cases, you will get the output is exactly integration of input and then divided by RC, by a time constant. So in the extreme case, if RC equal to 1, and your input will be, your output will be input integration and then minus sign. So in this case, if example will be if RC equal to 1, if VI equal to also say sine omega t, and what will be your VO? Well, it's minus 1 over 1 integration. Okay, if also VC 0 equal to 0. And then it will be integration of sine omega t dt plus 0 and equal to minus cosine omega t, or sine omega t cosine omega t is minus minus, it gives you positive. Yeah, that's cosine omega t. So you see? 1 over SARS. Yeah, you're right. 1 over omega, yeah. 1 over omega, you're right. Okay, thank you. Yes, you're right. So this is where your integration really does work. So the other example will be, okay, so let's see that you have this type of input. Now, the trouble to look at this circuit is that, well, there's a resistance in parallel with the current source. So the current source going in here, we don't know how much is going through 5K, and we don't know how much is going up to the capacitor. So that's where the trouble comes, even though we know the voltage at positive terminal and negative terminal is both 0, but to solve this kind of problem, um, volts, and the first thing you need to do is really convert this into a voltage source. Okay, so use this source transformation. So you can use this one. And this IS.
So wouldn't it be BS?
5K times. So it's going to be 5K times IS is the VS, right? You're right.
And wouldn't the equivalent be a voltage source, not a current source?
Yeah, when you use source transformation, it becomes a voltage source.
No, that I misread that. Plus and minus is 9. My mistake.
Yeah. So once you do this, and you find this is 0 and this is 0, right? And you can find the current again. So when that current goes to 5K, and then that current goes here. Okay, so let's say we're not going to go through the real process, but let's say assume that current I1, we're going to call it I1 here. Let's say I1 is DC, is 1 amp, and this C is 1 farad, and we see 0 is 0. You can see what happens now with the current going through. I'm just assuming the current going here is 1 amp. I don't, not looking at that. So this 1 amp goes in, it doesn't go into this one, so it goes up. It goes up through the C, and the current going to the C. What happens now? You guys already said? It's going to charge a capacitor, and then the voltage is going to go all the way. So basically, your VC. So your VC is going to be an integration of like 1 over C integration of 1 amp, which is constant, times dt. And because the initial voltage is 0, so now we got, so it's just 1 over C times T. Because that 1 amp is constant. So the integration of constant is T. And T derivative is 1. So because yeah. So as T increase, initially T0 is 0. As T increase, what happens to VC? It just shoot up. Until you saturate, right? Yeah. So ideally, it will just go up, up, and up until it saturates. So this is what we call an integrator. So basically, you can use this op amp and a C to form an integrator. Of course, the input can be a DC, it can be AC. It doesn't matter. The output will be integrating until it saturates. Or if it's AC, it's simply some sort of variation of AC voltage source. So this example we already did it. I mean, if you have a large RF, so what happens is that, yeah, probably we can skip this one because, I mean, we probably don't get to that. Let's do another one to do a differentiator. So a differentiator is the opposite of integrator, which of course is true. Now you can always use an inductor to do a differentiator, but you can also do a capacitor to do a differentiator. So the idea is that, let me see if I have enough slides. Okay. Let me do this one first, because if you have an op amp, like we did for the instead of using a C, we're going to use L, see what happens. Well, again, you find this 0, and also 0 amps here. Okay, so we find this current I1. So we kind of I1 equal to I over R1. So all the current going to equal to I2. And let's call VL. So VL is going to be the integration of the derivative of current L right? So then you have like 0 minus VO equal to VL. So therefore VO equal to minus VL. And so basically you can replace this one L di 1 over dt. And then we plug in those, and we plug in, yes, but I took same as I1. And I1 we already found is VI over R1. R1 is a constant. So therefore VO equal to minus LOR times dVi over dt. And here, of course, tau is LOR. And similarly, in the previous example, you have RC is your tau, right? So you basically, yeah, so you get this expression. So now we're going back. Instead of using an inductor, we can always also use a capacitor. But now we're going to flip the position between the capacitor and the resistance. So what happens, again, you guys know that we repeatedly use this one. So this 0 volts, so therefore this 0 volts here. And the current I, in this case, current I, going to the capacitor is going to be, you know, looking at C dV over dt, right? So that's the current going through the capacitor. And this V is VI. And all that current going through the R. So therefore we have 0 minus VO equal to I times R. So VO equal to minus I times R. Now I equal to minus CR dVi over dt. So you see again, this is our differentiator. So with input coming in through the R, you got the derivative. And that current again goes to R, so therefore you get this output VO is CR dVi over dt. You can, so far we wrote them in time domain. You can always write them into a frequency domain. So in frequency domain, basically you're gonna transfer that. In frequency domain, you can use VO like equal to minus CR times S VI. So what you're doing is you use this d over dt. You know, we also in the time domain, in the frequency domain, we have S equal to j omega. From time domain to frequency domain, you replace d over dt with S. I guess that's the beauty when you guys go into 420 and so on. You see a lot of them use S, so they use like interchangeably. Sometimes they use a P instead of S. So P means the derivative. So replace d over dt with P. You replace d like squared over dt squared with P squared. So they do this all the time. But simply, we're not going to go too much over here. But I just want you guys to understand that you can do an integrator or you can do a differentiator by simply manipulating the connections of capacitors in inductance and resistance in the circuit. But the bottom line is that you guys need to remember a number of different things. So for ideal op-amp, that's what we do in this chapter. And then the inverting amplifier, you get the output is negative. Yes. It is a differentiator, yeah. Yeah. I mean, here, you see your output, VO is a negative ROR dVi over dt. So it's a derivative of input. So it's a differentiator. Yeah. And the second one is non-inverting amplifier, which your output is positive. So usually your input is connected to the positive terminal. Now we always use negative feedback, okay? Regardless inverting or non-inverting, the feedback is always negative. And then we have a differential amplifier or difference amplifier. You guys learn how to do the instrumentation. And you got homeworks also like similar to that problem. Just don't get scared when you get like complex op-amp problem. Always go find where's the terminal. The two terminals are going to have the same voltage. And there's no current going into the terminal. If you remember these two things, it will make your op-amp circuit very simple, okay, very easy. And finally, we talk about integrator and differentiator. Okay. We're going to conclude this chapter at this point. Any questions? Or do you guys want me to do some more examples? Do you guys have problem like homework, something like you want? Okay. Now I'll look at the deadline of the homework for chapter 2. If it's too early, I'm going to extend it. I mean, bottom line is that before the first middle term, you got to have finished everything, otherwise you'll be too late, right? So I don't mind, giving you guys more time to do it. It's okay, yeah. Okay, so if no questions, I'm gonna upload the ones with the notes also, so you guys. Okay, so we're gonna go to chapter 3, and chapter 3 relatively short chapter, and we don't want to spend too much time here. But you do have some work that you can earn points towards your final, and also this just gives you a little bit of scientific understanding of semiconductors. Now we talk about op-amps and which is really ideal. But as we move on, we talk about diodes, BJTs, MOSFETs, and amplifiers, and so on. So we got to understand a little bit physics behind it. So this kind of give you some scientific background. The homeworks that you guys have to do to earn the points, and the contents is not in the middle term. So basically, depending how much time you guys want to spend, it's up to you. So in this chapter, we're going to go over like 5 different things. So we look at what is a semiconductor, how do you dope a semiconductor, how current flow is formed in the semiconductor, and how do you form a p-n junction. P is positive, N is negative. So p-n means positive and negative junction. And finally, we're going to go a little bit about the capacitive effect of p-n junction. Just when you have two metal plates together like this, what do you form? A capacitor, right? So when you have a p-n junction, which means you have one like metal on this side, because when you have a semiconductor devices, we have to connect those devices current to form some sort of outside loop. So those connections are through metal. So we put a metal plates outside the p junction, and we put a metal plates on the n junction. So those two metal plates together, they form some capacitive effect, which is capacitance. Okay, let's move on. So semiconductor, primarily, we talk about like silicon. Now, of course, today people talk about other semiconductor materials, like including silicon carbide, which is like a compound of silicon. They talk about gallium nitride, which is another compound. It's also semiconductor. And also even like diamond is a semiconductor. In life, we have insulators and conductors. So conductors, you guys probably know, like copper, aluminum, silver. Those are conductors. The most popular is copper, has a good conductivity. Aluminum is the second. It has not as good as copper, but it's cheap. So in areas, space is not a problem. We use aluminum because it's cheaper. In case where space is limited, we use copper. So copper is more popular than aluminum. But then on the other hand, you have insulators like wood, plastic, what is it? Air, yeah, air, sort of, yes. And then polymer, a lot of polymers, mica, rubber, those are insulators. Insulators do not conduct current. Epoxy, okay? Now, between positive and negative, like we need insulators, otherwise you will leak current, right? So, but in between, we have semiconductors, which means they're not conductors, but they're not insulators. So they're semiconductors. For conductors, for something to be a conductor, you need a lot of free electrons, like a copper. You got a lot of free electrons. When you apply a voltage across this copper, because there's a lot of free electrons, they're free inside the copper. When you apply a voltage, there's a potential, there's electric field, so it will move electronics in one direction. So that is the opposite of current direction. So current goes through. That's why it's a conductor. With an insulator, there's very little electrons in it. There's pretty much no electrons. So therefore, when you apply voltage, no current because there's no electrons to flow. So that's why it's called insulator. But in semiconductor, the electrons are in between. So it's not as much, but also it's not zero. It's not near zero. So for something to be a conductor, I think you need the electrons to be somewhere 10 to the 21 or something, okay? To be an insulator, you need to be less than like 10 to the 3 or something. But between 10 to the 3 and 10 to the 21, you get a lot of semiconductors. So the most popular one, as I mentioned, is silicon. So silicon. So silicon in natural form are bound together by atoms, like each atom has 4 like, yeah, I don't know. And then you have 4 electrons, but they're bound together because there's like a positive and negative, they're equal to each other. And all the atoms, they're connected, so they form like a bond. So we call this like silicon crystal. They have no free electrons. So nothing would happen if you apply voltage, it would not conduct current. That's the free, that's the silicon in its natural form. But when it is in the, what do you call it, like a negative 273 degree C or 0 K, those are true. But when you move back to room temperature, it's no longer true. When it's to room temperature, some bonds would break because the temperature rise create an energy. They call it energy gap between like the energy gap between atoms. So therefore, what happens is that some of the electrons are going to break away from the atom, and it goes somewhere. So when it breaks away from the atom, from the meter, you can see what happens is that you have a free electron somewhere, but then the one that with a broken electron also have less bond. So you only have 3 negative but 4 positive. So therefore, this one positive. So that positive called a hole. So it's like this electron was in a hole, so it's neutral. But when electrons goes away, so you got a free electron there, then that one becomes a hole. So we have free electron and a hole. But naturally, because the bond break, when the bond breaks, you got the total number of holes and the total electrons are still the same. And even though you got free electrons, but they're the same. So therefore, they're still not considered conductive. Plus, those electrons are not so many. They just some atoms start to break, but not enough to form a current. And even if there's enough, when you have current, they're going to jump back. So those break bonds are going to recover, so they're going to neutralize. Therefore, they're going to break, neutralize, break, neutralize. Therefore, there's no way you can conduct current. But what happens when we put impurity? So impurity includes material like phosphate or material like a boron. So those material, phosphate and boron, has a similar atom structure, but they have one, like in this case, we put probably a phosphate in here. Now, they are called, when you put this here, this atom are going to bond with the silicon atom. When they bond together, this one has a 5 positive. So when you have 5 positive, you got 4 this electrons. You see what happens? That free electron is free to move. So it's no longer going to bond back to the atom. So it's going to when you add this impurity, you got a free electron. So the whole, if you add like many this doping like material, you're going to create a lot of free electrons, and of course the number of electrons depending on how many atoms you dope into the material. So that process is called like doping. Now, if you add like another material like a boron, it has the atom has a 3 positive, and when you have 3 positive, it's going to attract the electrons back, so it's going to bond back. Now, because this is 3, you see everything else is 4, right? So you got a hole here. So this gives you a hole. So when you have a lot of this material doped, you get a lot of holes. So when you have a lot of holes, means that it will like need electrons. So when electrons goes in, it's going to neutralize. When you have electrons, they need holes. When you have holes, they're going to neutralize. So this process, doping, is going to create holes and electrons. So when you have this semiconductor doped, you like connect this a voltage source in a piece of semiconductor, you would not have current. Why? Because the electrons flow this way, the holes flow this way. Inside, they equal to each other. So basically, you see current inside, but there's no current outside because like inside everybody working this way and other people working this way, so it neutralizes. So there's no really no current. Okay, but it's going to create a E field. So what happens is that when you started to inject holes on one side, inject hole means really just inject positive, like you can think like a positive electron, and it goes in. So and then you form a current going like this way. Okay, if you inject a lot of holes into this and it goes this way, so you have current going this way. Now, if you inject electrons, now okay, so if you inject electrons, so what happens is that the electrons are going that way, but then the current direction is opposite to the electrons, right? So you also would have a current. So the idea that you need to either inject hole or you need to inject electrons. When we have material, we inject like a boron, we form N-type because they generate free electrons. So they call N-type, negative. I think you're right. Boron is P. Okay, yeah. Phosphate is negative. Okay, so okay, we don't have to. Well, I guess when you inject a lot of holes in the silicon, you get a positive. When you inject a lot of holes, electrons, you get a negative. So just to think it this way, the P-type has a lot of positive, like electrons, not electrons, it's a positive particles. And then the N-type has a lot of electrons. So this one, you put this together, like a miracle would happen. Because you got p-type, n-type, you put them together, you form a p-n type of material. It's called a p-n junction. So this whole thing is called a p-n junction. So you have really just the connection between these two is a junction. Now you guys think about it. This one has p-type material, which means a lot of holes, and this one has is n-type, has a lot of electrons. When you put this two, this has positive, this is negative. What happens to the electrons and the holes? They're going to move. They're going to move because they're going to attract each other. Because positive and negative, they're going to attract. So by attracting, the holes are going to jump to this side, and the electrons are going to jump on this side. So in the middle here, you form a region, it's called like depletion region, where they're going to neutralize each other. Okay, so this is really just the miracle for semiconductor. So you can see here, we can see the electrons are going to jump from this material to this side, and the holes are going to jump from this to this side. It forms like a depletion region. In the depletion region, if we look at the potential, and this is positive, okay? And then that's negative. So what is drawing here is that the potential started to increase, and here it got to maximum. So that's the electrical field. The electrical field.
So the middle is neutral?
The middle, well, the middle is neutral in the sense that the electrons and holes are neutralized. But now you have positive separated, negative separated by this neutral region. So therefore, there's electrical field there. There's a potential difference. So the potential is there. If you look at it in this region, the electron and holes are kind of neutralized. Therefore, this looks like there's no. They stop moving at some point. And then you start to have a potential between these two. So now, if we connect a voltage across this p-n junction, and you would see a very interesting phenomenon. Okay, so this is what we are saying about actual, like the field form. Look at they call the carrier concentration, the charge density, and in the book I didn't write any equations. In the homework there's something you have to calculate the total electrons and holes generated, things like that. You would have to plug in those equations. So when the voltage is generated, the next step is we're going to connect a voltage source with this p-n junction. So the first one is we are going to just have it open. Now, when you have it open, there's a positive hole moving this direction, and there's electrons moving this direction initially, but at some point it neutralizes, and there's no more current flow. So we call it equilibrium. In the equilibrium, there will be some holes on this side and some electrons on that side, and it form an electrical field in the middle. Let's go into the right hand here. We're going to apply a voltage positive on the P side and negative on N side. Now we know that initially there's already like electrons moving this way. Now when you connect a negative terminal to the N type, so when electrons move this way, the voltage source can provide electrons. So when the electrons start here moving, so electrons start going to move in. So electrons are going to move from voltage source all the way to here and go this way. Similarly, when positive moving to this direction, you have the positive voltage source to supply the holes that it's moving. So if you move 100 holes to here, and the voltage source are going to supply 100. So eventually you're going to have this current flowing because the holes are supplied by the voltage source, electrons also supply the voltage source. So therefore, in this, if you read the book, you'll find that there's two currents. There's a IS, there's an ID, but ID is much larger than IS. So therefore, ID minus S gives you the total current in this branch. So the current starts to flow. But if you flip the direction of the voltage source, if you flip the direction of voltage source, let's look at this side, what happens? Well, electrons move this way, but you have the positive side of the voltage source. What does it do? It drains the current, it drains the electrons as well. So which means initially electrons are already flowing this way, but you are draining the electrons to that way. So instead of supplying electrons, it attracts electrons. Okay, so once attract electrons, and this similarly, this are attract holes. So instead of having current, you're going to separate them more and more. So when you separate them more and more, basically, eventually, there's no current because at some point there's no current because it becomes another equilibrium. So
is neutral, or there's still a little bit left?
Well, it depends. And later on, when we talk about the xenon dyes, for example, it breaks the barrier and you start to have current flow. But before you break it, it becomes equilibrium. There's no current, and then all the electrons are gonna on that side. All the holes are on this side. They like look at each other. Okay.
Like a diode, it allows current, it allows voltage over a certain threshold in one direction.
Right. So we call this one reverse biased. So we basically having a voltage, reverse voltage, because our negative is connect to the P and positive connect to the N, so it's called reverse. But in this case, we call it forward bias. We call it forward bias, which means you have voltage applied to the positive and negative. So eventually, there's no current here, but there is current over here. And how much current would depend on, and I think in the next chapter, we're going to talk exactly how much current is ID. But you're right. So in this case, really, it is a diode. And it's like you're applying a voltage. In this case, so this is diode. So there is a current flowing this way, but there's no current in this way. However, in the middle one, if the voltage increase too much, it's going to break the bond. So therefore, what we call it, it's a breakdown. Once breakdown, how to exactly explain this phenomenon? But when it breaks down, this p-n junction is like is broken. So therefore, the current will be flowing through that p-n junction. It's no longer become like a barrier. So initially, it's a barrier because but I guess if the voltage is increased to some point, and it's no longer able to hold the electrons, so it start to flow. The reverse direction current has two purposes. One is that it can block current. And our one, of course, when we use it as a xenon diode in breakdown region, it has a fixed potential between positive and negative. Yeah. You can use it for circuit protection. Yes. Yeah. You can block current to going backwards. You can rectify currents. So that's why when we move on to next chapter, we're going to get into the Yeah, it is. But we're going to get into more detail about how to calculate the current in the diodes, how it relates to the thermal temperature, and so on. So if you have a forward biasing PN junction, and you can see this is the direction of the junction, and in the P region, what happens with the potential, and in the N region, then you have how much electrons, and then in the middle you have this depletion region, right? And then somewhere you have this somewhat equilibrium, and the theory of semiconductor is that by designing the thickness of the P and the N area, right? And also like the size, because the bigger that you have, the more electrons and more holes you can have, right? So the more current you can conduct. And also, depending on how much impurity you inject, you can decide how many electrons and how many holes in that diodes. In that each of the P and N type material. So you can build different semiconductor devices. And by putting multiple PN junctions together, we can form sort of BJTs and MOSFETs and so on. So those are going to be studied later. Okay, I think that's what we're going to cover today for the, okay. So basically, probably a little bit more about the current of the PN junction. If you apply a positive voltage, of course, your voltage is zero, the current is zero. If you apply more, this is current. But in practice, there is call this like a reverse current. It's kind of sort of like leakage current. It's very small. It's like in sub micro amps, basically close to zero. So this is how, like me, I draw the circuit. On this, you have this is the current going through, and then this is the current. So when I mentioned earlier, when the reverse current breaks down, there's a breakdown voltage. When it breaks down, this is basically just like a short circuit. So the current will increase with very little bit of voltage increase or increase a lot. And sometimes we use this property to build a Xenon diode as a like voltage stabilizing device, because the voltage is almost like constant, regardless how much current flows into that diode. Okay. So in this chapter, I think we want you to understand what is semiconductor, what's conductor, what's conductivity, what does impurity means, how to create holes and free electrons to form N-type and P-type material. And when you do that, you start to form drift current, diffusion current, all that kind, and then the electric field between the positive and the negative material, and put them together, build a PN junction. And apply voltage in the forward direction, you get current. In the reverse direction, you don't have current. But once the reverse voltage, you increase a certain level, it breaks down, and you get a lot of current. So that's the end of this chapter. And then next week, we're going to start with diodes. Okay. Yeah. If you guys, have questions, so far nobody have joined my office hours, but feel free to join in person or online.